This is Dr. Vermilio. In this lecture, we're going to continue our discussion of Kramer Chapter 5 on audiogram interpretation. And we're going to discuss the need for masking. Recall that masking is required when there is a possibility that the non-test ear will hear the sound, the test sound. This is the documentation of thresholds. This is an audiogram and our symbols for air conduction thresholds. You should memorize the symbol key. So the open circles represents unmasked air conduction thresholds. The X's represent unmasked air conduction thresholds. The triangle represents masked air conduction thresholds. So a right masked air conduction symbol means that the left ear received the masking noise. A left masked air conduction symbol means that the left ear was the test ear. The non-test ear was the right ear, and the right ear received the masking noise. We have, again, those bone conduction symbols that look like a sideways V. When they open to the right, that indicates an unmasked bone conduction threshold when the bone transducer was placed on the right ear. This symbol means, this bone conduction symbol, where it opens to the left, that is a left bone conduction symbol. That means that the threshold was obtained when the bone conduction vibrator was placed on the left ear. Again, no masking was used. And please realize this, that even if this shows a left bone conduction symbol unmasked, it could be actually that the right ear heard the tone, and this threshold is actually a reflection of the hearing on the right ear, not the left ear. So these are unmasked symbols. These are masked symbols. These brackets represent bone conduction thresholds when the bone vibrator was placed on the left ear and the noise was delivered to the right ear. And as long as masking was appropriate, then these bone conductions are thresholds are truly represent truly represents the hearing for the appropriate ear. So that really represents the hearing for the left ear. This symbol represents the hearing for the right ear. Whereas for the unmasked thresholds, it's not the case every single time that this left bone conduction symbol actually represents the hearing for the left ear. And we'll get more into that. Let's see, the average normal threshold is 0 dB across test frequencies. All of the thresholds on this graph or audiogram are above or poorer than the average normal threshold. Thresholds less than or equal to 25 dBHL are considered within normal limits. So we said something here that seems kind of strange. So we said 0 represents average normal hearing, but by convention we're going to say anything 25 dBHL or lower is within normal limits. So this is actually the average threshold for normal hearing, but we have a range also that we're going to consider within normal limits. So it's 25 or lower. And you know, anything above the level of the threshold is audible by definition. And anything below the level of the threshold is inaudible to the patient if the pure tone thresholds are real, if the patient wasn't malingering. Okay, recognizing the need for masking. Masking noise is used when needed to prevent the non-test ear from hearing the test signals delivered to the test ear. Clinical masking is the process of putting noise into the non-test ear while measuring thresholds in the test ear. These thresholds are called masked thresholds. One of my students asked me, well, you know, if masking is such a good thing because we know we're going to eliminate the participation of the non-test ear when we're doing the pure tone threshold test, why don't we always use masking noise? And the answer is, 1, it's not necessary. 2, it's extremely time consuming. A pure tone threshold audiogram for somebody with no need for masking might take us, I don't know, about 20 minutes. Air conduction thresholds, bone conduction thresholds, if the patient is relatively sharp and they're consistently responding spotting. Their responses are reliable. But a pure tone audiogram, bone conduction and air conduction, when you need to do a lot of masking, when there's always the risk that the non-test ear is hearing the tones, that could take you 2 hours or even more. And then if the patient's responses are not reliable, oh my gosh, 3 hours? That's just for pure tone thresholds. That does not include otoacoustic emissions. It does not include speech perception thresholds. It does not include the word recognition scores. It does not include tympanograms, the case history, acoustic reflex thresholds, all these other things, counseling, case history. So it's a very time-consuming process, and we can't mask for every threshold if we don't need to. Okay, so here's a happy customer. Notice that the right earphone is on the right side, the left earphone is on the left side. Red is right, blue is left. Sounds familiar. So the red earphone goes over the right ear, the blue earphone goes over the left ear. Test sounds are presented to the patient one ear at a time. We can do this with headphones. We can do this with insert earphones, with supra-aural earphones. We can't do this with a sound field speaker. We do not get ear-specific information with a sound field speaker. In this example, let's say that the patient is actually deaf in the right ear. Now, we don't know. We actually don't know this when we start testing. So we have a patient. We don't know that the patient is deaf on the right side, and we're going to start our testing. Now, which ear actually heard a 60 dB HL tone presented to the right ear? Now, let's assume that the hearing in the left ear is normal. The right ear is the patient is deaf in the right ear, and we delivered a 1,000 hertz pure tone presented at 60 dB to the right ear, and the patient says, "Yes, I heard that tone." Well, you know what happens? There's this thing called crossover. The earphone is actually vibrating the skull when it delivers the tone at 60 dB HL. It's vibrating the cartilage, vibrating the pinna, vibrating the airspace within the ear canal, which vibrates. It's vibrating the whole thing. So specifically, forget what I said about the airspace within the ear canal, because it doesn't matter, because that ear is deaf. It's not going to take advantage of that signal going through the TM and on into the cochlea. So the cartilage is vibrating. It also vibrates the bone and sends the signal through bone conduction to the cochlea on the other side. Again, we're presuming that the left ear is within normal limits. The hearing is good. So when the patient says, "Yes, I hear it," they're actually hearing the tone in the left ear that was delivered to the right ear through this process called crossover. So most likely the left ear heard this tone. The tone delivered by air conduction to the right ear crossed over via bone conduction to the cochlea in the non-test ear, or the left ear. In order to determine the real or masked threshold for the test ear, which is the right ear in this case, we'll need to present masking noise. It's also called narrowband noise at 1,000 hertz to the left ear, and then continue presenting the test tone at 1,000 hertz to the right ear. So masking noise goes to the left. That's the non-test ear. We're not interested in the threshold of the left ear right now. We're testing the right ear. Okay, there is a masking protocol called the plateau method that may be used to determine the true or masked air conduction threshold for the right ear. So here's let's look at this. This is a bone conduction vibrator used for bone conduction testing. This type of pure tone testing bypasses the external ear canal and the middle ear and tests the auditory system starting from the cochlea via vibrations from the bone vibrator, also called a bone oscillator. The bone vibrator will vibrate both cochleae at the same time. It is possible for a test signal to be delivered to the test ear, the right ear in this case, and for the patient to actually hear the tone in the non-test ear, the left ear in this case. Okay? So again, we can have crossover, and if there is a chance that the patient will hear the tone in the non-test ear, then narrowband masking noise must be presented to the non-test ear via air conduction. Check this out. Masking is always delivered via air conduction. The test tone will be delivered via bone conduction if it's for a bone conduction threshold, or via air conduction if it's for an air conduction threshold. Okay? So in this case we see the patient, the bone vibrator is actually behind the pinna on the right side, and then we have this funny skewing of the headset on top of the bone conduction vibrator headband, and the left earphone is going to the left ear. The right earphone is just sitting on top of the head. We're delivering masking noise to the left ear, which is the non-test ear, and we'll deliver the test tones through the bone vibrator on the right side. In the following example, pure tone testing for air and bone conduction thresholds reveals an air-bone gap for the right ear. This gives the impression of a conductive hearing loss for the right ear. Okay, in the following example, pure tone testing for air and bone conduction thresholds reveals an air-bone gap, in quotes, for the right ear. This gives the impression of a conductive hearing loss for the right ear. Question, is this air-bone gap real? In other words, are the bone conduction thresholds real? So here, this is from Kramer. I'm sorry I don't have the figure number for you, but it's in Chapter 5. And remember, these open symbols to the right indicate a right bone conduction threshold. So the transducer was placed on the right ear, and then when the and that's the threshold. And then when the right earphone was placed on the right ear, that's the threshold. So this looks like an air-bone gap. But wait a minute, the bone conduction thresholds for the left ear sure look a lot like the bone conduction thresholds for the right ear. Well, that's interesting. And then you have the left air conduction thresholds all within normal limits. So there's a hearing loss on the right. The question is, are these bone conduction thresholds for the right? In other words, is this really a conductive loss or is it a sensory neural loss? Well, after masking is conducted, and we're going to assume that the masking was conducted appropriately, then we see that the real bone conduction thresholds for the right ear are actually relatively equal to the air conduction thresholds. That means that this is a sensory neural hearing loss, not a conductive loss. Okay, so that shows you one of the reasons why we need to mask is in order to determine not only the severity but the type of hearing loss. So let's take this step by step. So bone conduction threshold opens to the right. That's unmasked. Opens to the right for the right when the bone vibrator is on the right ear. We do this protocol. Remember this thing, you know, the 3 or 4 ascending rounds. We look for the lowest level where we get a positive response at least 50% of the time. So this test run isn't necessarily for this. This is just for illustration. But that's what we're going to do. We're going to use the Houston-Westlake protocol, the modified Houston-Westlake protocol, from Drs. Carhart and Jerger in their paper from 1959, and we're going to obtain this threshold. Okay? So the pure tone threshold technique is conducted for both bone and air conduction thresholds. Here it is for the right ear. Notice the red color right there. That means the right ear. And then we do the same thing. So we do this Houston-Westlake protocol, and then we determine the threshold. We do the same thing for the left ear, bone conduction threshold, unmasked bone conduction threshold, and the left ear air conduction threshold. Okay, so that's how we get this. So the unmasked thresholds give an impression of a conductive loss. Unmasked air and bone conduction thresholds give the impression of air-bone gaps. This is consistent with the conductive hearing loss. However, it is not real. And then we show on the audiogram off to the right, masked bone conduction thresholds show no conductive hearing loss for the right ear. This is actually a sensory neural hearing loss. So why is it important to know the true type of hearing loss? Well, we need to tell the patient if they have a hearing loss, and if they have a hearing loss, we need to provide some sort of remediation or intervention, such as pure tone thresholds, such as hearing aids or a Baha device, possibly a cochlear implant in extreme cases. So the audiologist and physician will use this information to determine the type of treatment. And a conductive loss may warrant surgery in some cases, so we would not want to give a physician false information regarding the type of hearing loss. Okay, there's something called interaural attenuation, and that is the difference between the stimulus level delivered to the test ear and the amount that crosses over by bone conduction to the non-test ear. It's called the interaural attenuation. In other words, it's actually the difference in level from one ear and then as it reaches the other ear. So why is it important to know this during pure tone testing? Well, the answer is we need to determine the need for masking. And if we know about this interaural attenuation, that's going to help us make a determination in that regard. So the interaural attenuation that we use when we determine the need for masking is 0 dB HL. So we're going to assume that a tone presented at 50 dB HL via bone conduction here will be received also at 50 dB HL over here. In this case, we're going to assume that a test tone is delivered by bone conduction. Okay, in this case, at 10 dB HL. Will be presented to both cochleae at 10 dB HL. In other words, the amount that the sound is reduced as it travels via bone conduction is 0 dB, or the amount of reduction or attenuation of the test tone as it travels from the test ear to the non-test ear is 0, meaning there's no attenuation, 0 dB. Interaural attenuation for bone conduction is considered to be 0 dB for the purposes of the masking protocol. But know this, 0 dB in this case means no change in level between ears. 0 dB HL represents the average threshold for individuals with a normal auditory system, okay? So notice 0 dB, and then it doesn't say SPL or HL after it. This says 0 dB and HL. So 0 dB HL represents a level. 0 dB with no other indicator represents a difference between two levels. So if you're going to look at a difference between two levels, or if you're going to add two levels, we'll report, if you're going to look at a difference between two levels, it's in 0 dB. If you look at an absolute level that's equivalent to average threshold for humans, that's 0 dB HL. Okay, this is from a study that looked at the interaural attenuation for bone conduction. And notice for subject B, the interaural attenuation for 500 hertz is 0. But look at the interaural attenuation for patient or subject L at 500 hertz. It's actually 25. Or what about patients H and I at 2000 hertz? Interaural attenuation is actually 30 dB. So this shows us that interaural attenuation actually has this range. So here we see a range from 0 to 25. Over here it's 0 to 30. At 4000 hertz it's 0 to 30 dB. We use 0 dB interaural attenuation for bone when we determine the need for masking, just to be on the conservative side or the safe side. Okay, and I think I just said this. Studies of interaural attenuation for bone conduction show that the actual interaural attenuation for bone conduction may vary from 0 to 30 dB. For masking purposes, however, we will assume that the bone conduction interaural attenuation is 0 dB, just to be on the safe side. Interaural attenuation for air conduction, we're going to assume that it is 40 dB. So air conduction interaural attenuation with a supra-aural earphone is 40 dB. So if we have a tone presented at 1000 hertz at 60 dB HL to the right ear, if this ear was deaf, 60 minus the interaural attenuation, or the amount that the sound is reduced as it crosses over from one ear to the next. Interaural attenuation we're going to assume to be 40 dB. 60 minus 40 means that the sound will be received by the cochlea on the left side at 20 dB HL. So we're going to assume that the cochlea on the left side will receive the tone at 20 dB HL. All right, and so study this slide and get a hold of this concept that the interaural attenuation for supraaural earphones is 40 dB, or we're going to assume it's 40 dB. However, again, when you look at studies on interaural attenuation for supraaural earphones, you can see that the range is actually very, very broad. And look at these different studies. The interaural attenuation for 1,000 hertz presented through a TDH39 supraaural earphone is actually 57 to 66 dB, not 40. So there's a huge, huge range. So studies of interaural attenuation for air conduction with supraaural earphones show that the actual interaural attenuation for air conduction may vary from 40 to 80 dB. For masking purposes, however, we will assume that the air conduction interaural attenuation for supraaural earphones is 40 dB. Again, just to be on the safe side. So interaural attenuation now for insert earphones. Insert earphones that fit snugly into the ear canals if they're inserted correctly. We're going to assume that the air conduction interaural attenuation for an insert phone is actually 55 dB. So back to our example. What if we took a 1,000 hertz tone, presented it to the right ear, and we didn't know it was deaf, but it was presented to the right ear at 60 dB HL? What would be the level that would appear on the opposite ear? Well, a 60 dB HL tone minus the reduction, interaural attenuation for insert phones, we're going to assume it's 55 dB. That would mean that the sound is heard in the cochlea over here. Remember, it's detected via bone conduction. Via bone conduction on the left side at 5 dB HL. But studies that looked at the interaural attenuation for insert phones actually found a huge range. We assume it's 55, or we're going to use 55 to be conservative, but oh my gosh, look at this huge range. Sclair and Denenberg in 1987 reported 100 dB of attenuation at 250 hertz. Very, very interesting. 75. So we're going to use 55 to be on the safe side. Though I have been in clinics where they said to use 75. But we're going to assume it's 55 according to our text by Dr. Kramer. Okay, studies of interaural attenuation for air conduction with insert earphones show that the actual interaural attenuation for air conduction may vary from 69 to 100 dB. For masking purposes, however, we assume that the air conduction interaural attenuation for insert earphones is 55 dB. Again, just to be on the safe side. Interaural attenuation. So for bone conduction interaural attenuation, using a bone conduction vibrator, we're going to assume it is 0 dB. Interaural attenuation, when we use a supraaural earphone for air conduction thresholds, we're going to assume it's 40 dB. And then when we use an insert phone, we're going to assume that the interaural attenuation is 55 dB. When masking is required, which air conduction earphone would you rather use for testing? Would you rather use a supraaural earphone with an interaural attenuation of 40 or one with 55 interaural attenuation? And the answer is the insert phone. With 55 dB of attenuation, that means that there's less of a chance that the non-test ear will hear the sound. And then that reduces the need or the requirement for masking, which reduces our overall test time. Cross-hearing, when the test signal is delivered to the patient's test ear and it is audible in the non-test ear, this is called cross-hearing. Cross-hearing will occur when the interaural attenuation is exceeded, and if the pure tone signal reaching the non-test ear is greater than the bone conduction threshold of the non-test ear. Okay, and we'll talk more about that. And that concludes this lecture, part 2 on Kramer, chapter 5.